Hello everyone, welcome back to another Intel Minds video. In this video, we're going to be talking to you a little bit about integration, the beginning of integration, as well as the Riemann sum, which is where the original integral is derived through. Now, let's begin by imagining this function y equals x squared. Now, given that we have this point x equals to 1, how do we go about finding the area under the curve from 0 to 1? Now, one of the first things you may think about is we could approximate the area by drawing shapes under it, or by drawing triangles, maybe squares or rectangles to approximate that area. And if you were one of the people that thought that, you are precisely right. Let us begin by drawing rectangles that have their right corner lying on the function. What I mean is, you'll see in a second here, if I draw a rectangle like this, where its right corner lies on a point on y equals x squared. Now, if we draw successive rectangles that all possess the same feature, you'll see that over time, all of these rectangles are just over the area under the curve. They're actually more. The sum of all these rectangles will have this little bit that is over the area of the curve. But this allows us to see an upper bound for the number of rectangles. Now, if we dedicate this exact point that the rectangle corner touches the curve, we're going to declare this point as x1, this point is x2, this point is x3, so forth, and let us declare this x equals 1 point as x of n, where n is any arbitrary amount of number, and this is n represents the number of rectangles that we have drawn. Therefore, we can draw that the sum, let's call it Sn, of the areas of n amount of rectangles as S of n is equal to, remember, so the height of each rectangle, 1 over n squared times its base, 1 over n, plus 2 over n squared times 1 over n. Remember that each of the rectangles possess the exact same base of 1 over n, which is just our point given here is our 1 divided by the amount of rectangles there are, which is the base, and times a height, which is going to be given as, remember, this is squared because our function is y equals x squared. And we're going to keep adding up these rectangle sums all the way until we get to n over n squared times 1 over n. And imagine this. Imagine if we factor this or expand this, we're going to get 1 over n cubed. And if we expand this, we're going to get 2 over n cubed. So in essence, we could simplify this. We can simplify this by subtracting out 1 over n cubed. And writing this as plus 2 squared as a sum of squares. And now we can substitute in here the sum of squares formula, which is, if you quick look through your textbook, will give you that it's n over 6 times n plus 1 times 2n plus 1. Further simplification, see that this is going to be continued to 1 over n cubed multiplied by n over 6, 2n squared plus 3n plus 1. Then it's going to result in n over 3, n cubed over 3 plus n squared over 2 plus n over 6. And this is going to equate to 1 over 3 plus 1 over 2n plus 1 over 6n squared. All right, so this is going to be our upper bound for the area under this curve. Now, let us have to think, all right, if that's the maximum, what's the minimum, right? So I'm going to draw back in our graph from before. With this point at xn equals 1. Or actually, this time we're actually going to look at it a little bit differently. For our lower bound, we're going to draw rectangles that have, instead of what we drew before, which is like this, where the right corner was lying on the curve, on the function, and it has a little bit over. This time, we're going to be drawing rectangles that have the left corner lying on the function, like so. This way, we'll see that there's this little area that is actually not included, and that the sum of these rectangles are actually less than the area under the curve. Now, if you let our first point be 0, our x1 be 0, and successive points are x2. So instead of our first point being x1, which is actually some defined x value, our x1 is now actually going to be 0, and our xn value, let's just keep drawing rectangles here, our xn value is going to be 1 right before our value of 1. So whereas before our xn equal to 1 and our xn minus 1 was here, we now have our 1 is we now have the xn value in the place of where the xn minus 1 basically shifted all the values left 1. As you can see from the x1 is now moved to 0. So that is basically what we've done here. Now, if we map out the sum, get xn is equal to, well, our first rectangle would have a height of 0. Multiplied by, remember, the bases of each one are the same. And you may be wondering, why are we doing this? Like, this looks like almost the exact same, aside from the fact that we shifted over all of our heights 1 over. Well, you'll see why in just a moment here. All the way until, remember, our last value is actually going to be n minus 1 over n squared times 1 over n. Okay? That's going to be our last rectangle. All right. So, we're going to factor out the 1 over n cubed. We're going to get 1 squared plus 2 squared plus 3 squared all the way until plus bracket n minus 1 squared. And now you might be looking at it, oh wait, that's an n minus 1 squared at the end. That's not an n squared at the end. So now if we again apply our sum of squares formula, we're going to see that it's going to be 1 over 6 of n over 6. This time we're going to get n minus 1 to n minus 1, as opposed to the n plus 1 to n plus 1 before, since our last value is this n minus 1. So, to do further simplification, we're going to see that 1 over n cubed is going to equal to, well, we can factor in this n actually into here, which is going to give us n squared minus n, 2n minus 1. And move it over here. N cubed over 6 bracket 2n cubed minus 3n squared plus n. We're just going to simplify to 1 over 3 minus 1 over 2n plus 1 over 6n squared. And this is just slightly different from what we had before, which was 1 over 3 plus 1 over 2n plus 1 over 6n squared. So we see that the signs here are switched. So whereas this is our upper bound, this is our lower bounds. All right. So we are getting close to the ending here. So rewriting this, we can write 1 over 3 minus 1 over 2n plus 1 over 6n squared is less than the area, well, since this area be the area under the curve, which is less than 1 over 3 plus 1 over 2n plus 1 over 6n squared. And since we know that the limit as n approaches positive infinity of 1 over n is equal to 0, and the limit of n approaches infinity of 1 over n squared is equal to 0, then we know that these values are going to approach to 0. They will get smaller and smaller as n gets larger and larger, and as n increases, you'll see that the area will slowly approach one third, which is, since this makes sense that the area is equal to 1 over 3 square units. So, to summarize, we can let f be some positive value function on the interval of a less than x less than or equal to b. We subdivide the interval into n rectangles, equivalent rectangles, equal subintervals of width. Subdivide n equal rectangles. Oops. Rectangles of width of x, which x is equal to the upper bound minus the lower bound over n amount of rectangles. And so that the area of any rectangle, if we choose some point x of k, which is the kth interval where k is equal to 1, 2, 3, all the way to n, and we construct the rectangle of height of f of xk. Therefore, we can determine that the area of any rectangle is equal to f of xk times the difference x, which is the width. One final statement here I'm going to write for you guys is that the sum Sn can be written as f of x x1 delta x plus f of x2 x all the way to plus f of xk of x. This can be written as the sum of n rectangles of k equals 1 to start with, of f of xk delta x. And this sum approximates the area A of the region bounded by y equals f of x and the x-axis between A and B, and this is called the Riemann sum. As the number of subintervals n, which is the number of rectangles, increases to infinity, the Riemann sum becomes an increasingly accurate estimation of the area, which is A. The sum approximates the area of the region bounded by the graph of y equals f of x and the x-axis, and is called the Riemann sum for f. As n increases without bounds, the Riemann sum Sn will become a better and better approximation for the area. And we can calculate the area A bounded by a continuous curve and the x-axis as the limit of the Riemann sum, as written like so. For any choice of points. And that is the Riemann sum and an introduction to integrals.